Good morning. Thank you very much for turning up for this early morning session. We are all in Amsterdam. City doesn't sleep. Tourist doesn't, definitely. And, a 9 a.m. session is generally not the most pleasant one to attend. So thank you very much for coming up here in good numbers, and I hope that this will be worth your time. So my name is Kamran Naqvi. I work for Broadcom, based in the UK. And in this session today, I can see some of the familiar faces, so I will be repeating some of the stuff I presented earlier this year on a couple of presentations, but there will also be some other material that will be new, which is more specific to SONiC. I'll start by talking about what are the different AI networking fabrics out there. Most of you would be familiar. This is just to level set. But I would also highlight what we are doing or where SONiC is already working and where we as a community need to work to enable those use cases for SONiC. I will then talk about what makes AI networking unique. I'll try to make it a quick session because I think I've at least touched it on a couple of occasions already. I'll give you a comparison of CLO and rail optimized design supported in SONiC for AI and how they help. I will point you to a reference design document that we have. At the end of the presentation, you will see there is a link, there's a barcode that you can scan and download the document. So I will not spend too much time on those topologies that I have, those designs I have, and I'll spend a bit more time on the SONiC enhancements for AI networking. Okay, what are the special things we have introduced in SONiC which makes it suitable, not just for all the data centers, but specifically for the AI workloads? Because as most of us know, AI workloads are different from the traditional data center workloads. And if we have time at the end, and I noticed that I started a little bit earlier, so maybe I can have a couple more extra minutes. If I do have time, I will talk about a little bit about Ethernet for scale-up networking. What are the capabilities required for scale-up? And for inter-DC, what is the use case there? Why inter-DC is a separate use case, and what we can do there as a SONiC community. And that will be my presentation. So let's make a start. So if you look at an AI network, there are 4 distinct networking fabrics. You can think of them 4 different networks, right? Out-of-band management, well, everybody knows about it. SONiC already works there. Front-end fabric, that is our traditional data centers, right? SONiC is a very good player in our traditional data centers. It's been doing it for many, many years. We at Broadcom, we use SONiC everywhere in Broadcom. In our 10 of our data centers, we use SONiC. We have now over 10,000 switches running SONiC. Various use cases from campus to data center and so on. Storage fabric, this needs some special capabilities to support specifically around RDMA, around Rocky. We have enabled this use case now for I think 2-3 years, and there are many of the customers are in production with SONiC on their storage fabric. Backend fabric is where the magic happens, right? So the backend fabric of an AI network is a different type of network. That is where GPUs to GPU communication happens, right? That is where you're running your training models, which need loads and loads of compute, which needs loads and loads of GPUs, where the communication is very different from the traditional networking. And I'll say a few things about it. Rest of my presentation, barring the last 1 or 2 slides, will be on the backend fabric. Now, within the backend fabric, there are different types of networks. That's where I'm double-clicking on this today. So within the backend fabric, there is something called scale-up network. So what is a scale-up network? That is the network, well, you have GPUs within a server or within a rack. The network which connects your GPUs within a server, this is called your scale-up network. Now, most of us are familiar with NVIDIA, for example, right? Well, I used N words here. There you go. The NVIDIA GPUs, probably the most popular, you typically get 8 GPUs, 4 GPUs, but the most popular form factor is 8 GPUs within a server, right? Now, these 8 GPUs need to talk to each other. They need some sort of network. That network is scale-up network. In case of NVIDIA, what is that technology there? NVLink, right? In case of AMD, this is Infinity Fabric, right? Or also you can also use Ethernet there. We at Broadcom believe Ethernet is the right network for scale-up networking as well, and I will talk a little bit about that. Now, scale-up network, as I said, GPUs within a server or within a rack. The scale-up network scale is increasing. We already know, you must have heard about NVL72, where you have 72 GPUs within a rack, and they are all connected with a scale-up network. We believe this is going to increase. From 72, it will go to 128, to 256, to 512, and so on. So that is an area which is growing, and that is an area where at this point, SONiC does not have a play. We believe we can have a play in the scale-up network as well. Okay, the other area, the other part of the backend network is called scale-out fabric. Now this is the fabric, this is a network which is connecting GPUs between different racks, different servers, right? Scale-out network is where we have been playing for a long time, and that will be the main focus of my presentation today. But there is another area as well, and that is inter-DC. So scale-out can be within a data center, or scale-out can be between the data centers. Now, if in case you are wondering, why do you need to have scale-out between two data centers? Why can't you just make a very big data center with lots of GPUs? Answer is, one of the main reasons is power, right? If you have a 10 megawatt data center, guess how many GPUs you can have in a 10 megawatt data center? So approximately, one GPU need approximately 1500 watts when you include everything that you need to support that GPU, the server, the networking, the power and cooling and everything, which means a 10 megawatt data center will only house 6,000 GPUs, right? What if you want to build an 8,000 GPU cluster, 20,000 GPU cluster, 100,000 GPU cluster? You cannot build it within a data center, right? The biggest we have seen is 100,000 within a data center, and people are already talking about 1 million GPU cluster. You cannot build a 1 million GPU cluster in one data center. You definitely need to connect many of these 50, 60 watt data centers together. When you are connecting data centers, when you're building a scale-out fabric over 100 kilometer, 50 kilometer distance, the requirements change. And that is where I probably won't have time to talk about it in detail today, maybe in my next presentation. But I just want to highlight that that is another area where we as a SONiC community do not play today. So this inter-data center and this scale-up, that is where we do not play, and that will be my call to action. That's my last slide that I've already discussed now. Let's talk about scale-out within the data center. Okay, so what makes AI networking, this GPU to GPU communication, different from our traditional data center communication? Very quickly, 3 points. Point number 1, this GPU to GPU communication within the data center, you have small number of flows because you have limited number of GPUs, but you have very long-lived flows, right? And they are very high bandwidth flows. So what is lacking there is entropy. What is lacking there is variety in the application. And when we apply a traditional networking model here, we will struggle because we will not be able to load balance this traffic properly, right? We do load balancing using what? ECMP, right? We can only do ECMP when we see many different flows. Flows are hidden here, and I'll show you later on. Flows here, if you look at the 5 tuples, you'll probably see a couple of flows. Whereas, within it, there are 20, 30 flows. So the entropy, because it's RDMA traffic, the entropy is within the RDMA header, not in the standard 5 tuples, right? So that is why load balancing is a struggle because of lack of entropy. That's point number 1. Second point, because this is RDMA traffic, this is it's sensitive to packet drop, and RDMA has poor retransmission algorithms. What it means is that a single packet drop will result in a large amount of data being retransmitted, which means that the effect will be much bigger. And why it is happening? Because RDMA has a very poor retransmission algorithm. Under UEC, we have improved it. So UEC 1.0 specifications are already out since June. You can read it. We have a new transport protocol there which improves on it. Okay. The third point is what we call this tail latency. As you can see, these flows are synchronous. Oh, this microphone. Can you still hear me?
Yeah, we'll go on.
Okay. Not many people listen to my recording anyways. My wife does, Sometimes my boy as well, when he listens to my voice, he sleeps better. So yeah, it's useful. Okay. What I'm trying to say here is these are synchronous flows. So if you see here, I can use this actually. So this first GPU completes its job here, the second completes its job here, but they do not go on the next cycle. Why? They are waiting for everyone to complete their job. They are synchronous. When everybody completes their job, then all of them start again. What it means is a single slow flow slows down everybody, right? And that is a killer for your job completion time. So if you apply your traditional networking models on AI networking, network will become a bottleneck. And that is what many people have seen. These are the slides I've used a couple of times. So I'll go very quickly here. Where in the network we see those problems happening? What are those problems? Number 1 is transient oversubscription. If you have an oversubscribed network, you will hit this issue. Generally, we see now, even on the storage side, people are not making oversubscribed networks. So I think we are okay there. Flow collision is a big problem. This problem happens. Did you notice that there is this synchronous nature of the traffic? Every flow, all the flows start together. Can we turn this on? So flow collision is a problem. So flow collision happens when you have 2 or more elephant flows mapped to the same link. You'll see congestion. They were mapped at the same time. So when they were mapped, link was free, and there you go. Now you have 3 flows going on the same link. It is oversubscribed. There is congestion. Link failure happens. We can't do much about it, right? We know that the optics are flaky. Optics will fail, and that will be an issue. Incast, once again, nature of the traffic. Thank you, sir. Can you hear me okay? All right. So incast happens when multiple GPUs are trying to talk to one person. So if 3 people are talking to me, of course, I will struggle. No matter how much buffer I have as a GPU, right, or as a switch, if 3 people are sending data to me, at some point I will start dropping the traffic. That is called incast. We need to do something about it. And what we can do about them? So for flow collision, we at Broadcom believe you need a better load balancing mechanism, right? And we have 2 approaches there. Approach number 1 is packet spraying, which we do in our Jericho line of family. With the packet spraying,
what we say, you can say it's a marketing term. We say you can get perfect load balancing. By the way, this is a Jericho 3 AI silicon, which kind of support this type of mechanism. I love posing for pictures. So when you're using that technique, you get very good load balancing. The other one is this cognitive routing, right? With cognitive routing, this is like enhanced ECMP. I'm going to double click on it because this is the capability we built in SONiC as well. So we have certain features in SONiC now, which makes it do better ECMP, right? The cognitive routing. And I'm going to talk about that. Okay. And for incast, we believe the best way to manage incast is to have a credit-based flow control. This is the feature that we proposed to UEC. It has been accepted. So in UEC 1.0, you will see there is a credit-based flow control mechanism. It's standardized now. What it means is that if you want to talk to me, and if you want to talk to me, I'll say you have 10 credits, you have 12 credits, right? So when I'm issuing credits, that is based on the capacity of the receiver. I know what is my capacity to receive the traffic. So there won't be any congestion within the network, which means there won't be any head of line blocking and those type of issues. Okay. Now, these are the two different solutions that we provide from Broadcom side. The one on the left-hand side, that is the Jericho 3 AI that I already showed you. The other one is Endpoint Fabric. We introduced this with Endpoint Schedule Fabric with Tomahawk 5. This is the solution which is enabled on SONiC. This is the solution which is probably the most deployed backend fabric out there at the moment. With the Endpoint Schedule Fabric, NIC and the switch work together. That is why we call it endpoint schedule, because the endpoint is also playing a part there. ECN, PFC, those type of features run from NIC and switch, and they talk to each other and they make it happen, right? There are some additional capabilities at that level which have been introduced by UEC. I will be talking about them at the end. You can get that type of solution. As I said, you can run it on SONiC, and you can get that hardware from nearly 10 different providers, from Dell, from EdgeCore, from Eufy, and so on, and OEMs like Nokia, like Arista, Juniper, and so on. Right. For Endpoint Schedule Fabric, the latest kid on the block that we have is this Tomahawk 6 fabric. So with Tomahawk 6, this is a 102.4 terabit silicon. This is the massive silicon. This is the biggest bandwidth, highest bandwidth silicon in the world as we stand. Everyone else is at half the bandwidth. This is double the size of bandwidth of any silicon, Ethernet silicon in the world as we stand today. So Broadcom is keeping our tradition of being the first. I'm sure all our worthy competitors will get there, but we are, like always, Broadcom is one generation ahead of everyone. Okay. Now, what is the benefit of having a 100 terabit silicon? You have double the bandwidth. So what? I can go to competition and buy 2 switches, right? That is, it doesn't work like that. Most of you already know that. Okay, I do not have that slide here. Yeah. I knew it was 20 minutes, so I skipped some slides and I missed an important one. What happens is, if you have a 100 terabit silicon, let's go back. If you have a 50 terabit silicon, so if you're making a network, a GPU network, a backend network fabric, with any silicon in the world other than Tomahawk 6, whether it's Broadcom Tomahawk 5 or one of our competition, if you have a 51.2 terabit silicon, you can build a 2-tier network with up to 8,000 GPU. If you want to build a network with 8,200 GPUs, you will need a 3-tier network. You with me on that? Yeah. There are many customers who want to build more than 8,200 GPU cluster, right? Specifically, it is 8,192. So if you want 8,193 GPU in your cluster, you need to go with 3 tiers. and bigger, right? With Tomahawk 6, you can build the architecture that we propose in the document, and you will see that you can build 34,000 GPU cluster in 2 tiers. If you look at the competition, you will need at least 3 tiers. What happens when you have 3-tier network? And there is no Broadcom magic in it. It's just calculation. It's just if you have 100 terabyte silicon, you can build a very large cluster in just 2 tiers. So what is the difference? If you look at this slide, right? So if you build a network with 3 tiers, it will use a lot more optics. There are a lot more connections there. Optics are probably more expensive than the switches themselves, right? So it is huge. You have a lot more latency. Now there are 3 hops involved, right? You will be, of course, be using more switches. There will be more power. It will be difficult to load balance that as well when you go into 3 tiers. So there are a lot of benefits of having this 100 terabit silicon. There has been some discussion in the past about InfiniBand, so I'm just keeping this slide. Now, I think most people believe that Ethernet is the right way to build backend fabrics. There was a debate a couple of years back. Ethernet has won that debate already. This slide shows that how Ethernet outperforms InfiniBand for AI jobs. This is the job completion time, and Ethernet is, in this case, 10% better than InfiniBand for job completion time at all the message sizes which matter. The other thing is we are also better in failure recovery. We can recover much, much faster compared to InfiniBand, 30 times faster. This is the worst condition. In the best possible scenario, we can recover 43 times faster than InfiniBand. So once again, Ethernet is a much better technology for AI networking. Now, why it is important for AI? Because of that synchronous flow, because of, if you lose, if one flow is slow, it slows down everybody, right? So you want if there is a failure, which will happen in your network, you want it to recover very, very quickly. Otherwise, you're going to have a very detrimental effect in your network. Everybody with me on that? Okay. So, and all the bigger networks built in the world, 7 out of 8 megascalers, they use Ethernet for their AI networking and not InfiniBand. How much time I have? I think I'm good. Ready? Right? Okay. All right. So I'll skip some slides. God, I speak slow. All right. So what are some of the capabilities in SONiC which make it very suitable for AI networking? Remember, I talked about load balancing is a big issue because there is lack of entropy. If you look at a traditional data center, you will see ECMP was enough. You were looking at the 5 tuples. You were looking at the port numbers and the protocol number and the source and destination IP, and it works. What I'm trying to show here is, look at this scenario. On the top, it looks like 2 people are talking to each other, G1 talking to G3, G4 talking to G8. But within those flows, there are multiple queue pairs. There are multiple sessions there, right? The entropy is hidden within the BTH header, within the InfiniBand header. Our traditional networking will not look at it. SONiC, we introduced something in SONiC called user-defined field, UDF hashing. Without UDF hashing, you can see that we are only using 2 paths. There are other links available. They are not being utilized. Why? Because networking devices using traditional technology just see them as 2 flows and they use 2 links. What we do with UDF hashing is now we can include destination queue pair as part of your hash calculation. And now you can see that there are multiple flows ongoing and you should be able to do much better load balancing. So what I'm trying to show here is that now you can use more of the links, all of the links, and that will give you better load balancing. The other technique we use is called adaptive routing. Once again, it's available in SONiC. There are 2 ways to do adaptive routing. One is a packet spray option, where you will be spraying all the packets of a flow. The challenge with that is you need to reorder it at the other end, at the destination. Now, once you have these UEC compliant NICs available, which will be available later this year, this is not a problem. Your NICs will be able to reorder them very quickly. We have something called out of order data placement as part of UEC. If you do not have those NICs, then this technique, you will struggle with this technique. You will have to use this flowlet spray technique, where what we do is when we look at a flow, we try to identify if there are gaps between the packets. And if there is a flow where there is enough gap between the packets, we call them different flowlets and we spray them across different links. In this case, you do not need to reorder the packets. So you have the load balancing and you're using most of your links and you still do not have to reorder. So these are some of the capabilities which were not there in SONiC, which were introduced as part of this AI networking initiative. Last thing I want to leave you with is that scale out is one thing, but scale up within the rack, that is a very easy network, right? There are certain capabilities which are required in scale up where you need low latency. We didn't have it in Ethernet. Now we do. We have a 250 nanosecond silicon available with Tomahawk Ultra, right? It requires optimized header. That is something that Ethernet silicon, Tomahawk Ultra can do. We as a SONiC community need to enable these features on SONiC so we can use SONiC for the scale up requirement as well. This link level retry and credit based flow control, these are the two things which were introduced as part of UEC. I don't have time to go in detail, but they are about reliability, how you can retransmit packets at the data link layer. And the last thing I want to leave you with is that when you talk about scale out across the data centers, that is where you need certain other capabilities of buffering, support of ZR plus optics, and so on. Some of those capabilities are already in SONiC, but there are other capabilities that we need to develop as part of SONiC community. So for SONiC, future is bright. I heard from, in the last keynote from Meta, they said, we are at 1 percentile of where we want to go. This AI networking, people call it AI, an AI bubble, but still for the next few years, there is going to be a lot of investment, a lot of deployment on AI. We can take SONiC to a next level by enabling SONiC for these two use cases. This is the barcode that you can use, QR code that you can use to download the document that I was talking about for AI reference models. Thank you very much for your time.